Have you ever wondered, in the vastness of the cosmos, how it all began? In the grand scheme of everything, we are but tiny specks, floating on a blue marble in a cosmic sea that seems to stretch into infinity. Yet, our curiosity is as boundless as the universe itself, propelling us to seek answers to the deepest mysteries of existence. One of the most intriguing questions that has captured the human mind for centuries is the origin of the universe. Enter the Big Bang Theory, the cornerstone of modern cosmology. It's not just a popular television show, it's a scientific explanation that paints a picture of our universe's birth and its evolution over nearly 14 billion years. The Big Bang Theory proposes that the universe began from an extremely hot and dense point, a singularity, and has been expanding ever since. This theory isn't merely a wild guess, it's supported by a wealth of scientific evidence from various fields. Observations of distant galaxies, cosmic microwave background radiation, and the abundance of light elements all point towards the Big Bang as the most viable explanation for the universe's origin. But let's clear up some common misconceptions. The Big Bang wasn't a colossal explosion, nor did it occur at a particular spot in space. Rather, it was the moment when all space, time, and matter as we understand them came into existence. So, it's not that the universe began in the Big Bang, it's more accurate to say that the universe is a product of the Big Bang. Now here's an interesting thought. If the universe is continuously expanding, what is it expanding into? Well, that's a question that even the brightest minds are still grappling with, and it's one of the many reasons why the Big Bang Theory, despite its widespread acceptance, remains a subject of intense debate and research. So let's dive into the cosmic timeline and unravel the mystery of the universe's birth. Imagine a universe so hot and dense it was nothing like what we know today. This was the beginning of everything, the dawn of our cosmos, dating back nearly 14 billion years ago. Our universe was born from a singularity, an entity so incomprehensibly small and infinitely hot, it defies our understanding of physics. This singularity was not in space, but rather space was inside it, a point so dense, so hot, that it contained all the matter and energy that would eventually become our universe. And then, in less time than it takes to blink, the universe began to expand. This wasn't an explosion, as the term Big Bang might suggest, but an extraordinary expansion, an inflation that stretched the fabric of space itself. Picture for a moment a balloon being blown up from a tiny speck to an enormous size in a fraction of a second. That was our universe, rapidly getting larger and cooler. As our universe expanded, it cooled down, and the fundamental forces of nature as we know them began to take shape. First came gravity, the force that pulls matter together, followed by the strong nuclear force, which binds the protons and neutrons within an atom's nucleus. Next was the weak nuclear force, responsible for radioactive decay, and finally, electromagnetism, the force that lights up our lives, literally. But this was not a peaceful time. The universe was a hot, chaotic soup of particles colliding and interacting, forming and annihilating. As it cooled further, particles began to combine, forming the first atoms, the building blocks of everything we see today. The early universe was a place of extreme conditions, unlike anything we can replicate today. Yet from this fiery, chaotic birth, our universe evolved, giving rise to galaxies, stars, planets, and life itself. In this dense heat, the universe's first moments were truly extraordinary. As the universe expanded, it cooled, paving the way for the formation of matter. Imagine the universe as an enormous cosmic kitchen, where the ingredients for everything we see today were being whipped up. In the first few minutes following the Big Bang, the universe was a seething hot, dense sea of energy. As it expanded, it cooled down, and this cooling allowed the first subatomic particles to form. These particles included protons, neutrons, and electrons, the building blocks of atoms. Now, fast forward a few 100,000 years. The universe had cooled down enough for these subatomic particles to combine and form the first atoms. Hydrogen and helium, the lightest elements, were the first to form. These atoms were like the first bricks in the construction of the universe. But here's the thing. Atoms alone weren't enough to form the stars and galaxies we see today. They needed to clump together and collapse under their own gravity to form the first stars. So our cosmic kitchen was now churning out a hot, dense stew of atoms and stars, slowly cooking up the universe as we know it. Amidst all this cosmic evolution, there's an interesting phenomenon that we need to talk about: the cosmic microwave background radiation. This is the afterglow of the Big Bang, a kind of echo from the past. It's like the heat that remains after you turn off your oven, a remnant of the initial high temperatures. This radiation permeates the entire universe, and it's a key piece of evidence supporting the Big Bang theory. So, from a hot, dense point of energy, the universe expanded and cooled, allowing subatomic particles to form, which then combined to form atoms, which in turn clumped together to form the first stars. And all the while, the cosmic microwave background radiation was there, like a cosmic heartbeat, reminding us of our universe's fiery birth. And from this primordial soup, the universe as we know it began to take shape. Fast forward to today, billions of years later, our universe is still expanding. This isn't just a claim made by scientists, but is supported by substantial evidence. One of the most compelling pieces is the phenomenon of redshift. When we gaze at distant galaxies through a telescope, we notice the light they emit is stretched out, appearing more red than it should. This is because these galaxies are moving away from us, and the universe is stretching, causing the light's wavelength to lengthen and appear more red. In the same vein, the cosmic microwave background radiation, or CMBR, provides another piece of the puzzle. Discovered by accident in the mid-20th century, the CMBR is the afterglow of the Big Bang. It's like a snapshot of the universe when it was just 300,000 years old, and it's the oldest light we can see. Additionally, the abundance of light elements in the universe, hydrogen, helium, and a dash of lithium, aligns perfectly with predictions made by the Big Bang theory. These elements were cooked up in the hot, dense conditions that existed just minutes after the universe's birth. But remember, our universe isn't just made up of what we can see. There's also dark matter, an invisible substance that doesn't interact with light but has a gravitational effect on galaxies. And then there's dark energy, a mysterious force that's pushing our universe to expand at an accelerating rate. While we can't see these dark entities, their effects are observable, further supporting the Big Bang theory. The Big Bang theory doesn't just explain our universe's birth, it also gives us clues about its future. As we continue to study the cosmos, each new discovery brings us one step closer to understanding our origins and perhaps our destiny. The universe today is a testament to the Big Bang, an echo of that first momentous explosion, and a hint at what's yet to come. Despite its success, the Big Bang theory doesn't answer everything. In fact, it leaves some tantalizing mysteries unsolved, poking our curiosity as we stand on the edge of the cosmic unknown. For starters, the theory doesn't explain what caused the Big Bang in the first place. It describes the aftermath of this colossal event. But the trigger? The spark that set off the most significant explosion in history? That remains a mystery. Some propose a quantum fluctuation, others a collision of multidimensional brains, but the truth is, we're still guessing. Then there's the issue of singularity. The Big Bang theory suggests that the universe started from a single point of infinite density and temperature, but our current understanding of physics breaks down at this point. It's like trying to divide by zero. The equations spit out infinity, they sputter and cough, and we're left scratching our heads. Infinity in physics is a sign that we're missing something crucial, a piece of the puzzle that's still out of reach. Next up, the enigma of dark matter and dark energy. They make up about 95% of the universe, but we can't see them, can't touch them, can't detect them in any direct way. We know they exist because of their gravitational effects on the universe, but what they are remains hidden in the shadows. The Big Bang theory doesn't shed light on these dark constituents of the universe. And finally, the fate of the universe. Will it continue expanding forever? Will it eventually collapse in a big crunch? Or does a more exotic fate await us? The Big Bang theory is silent on these questions. It tells us where we've come from, but not where we're heading. The Big Bang theory, while comprehensive, is still a work in progress, inviting more exploration and discovery. It's like a map with blank edges, marking the boundaries of our knowledge and beckoning us to venture beyond. And that's the beauty of science. The unanswered questions are not a barrier, but a gateway to new understanding. So, there you have it, a journey from the universe's birth till today. We started with the Big Bang mystery, traveled back to the beginning of everything, witnessed the cosmic evolution, and ended up in the universe as we know it today. We also pondered over some unanswered questions that continue to intrigue us. Now here's a question for you. How do you think the understanding of the Big Bang Theory can change our perspective about our existence? Share your thoughts in the comment box.